In effetti abbiamo pensato di averla uccisa perché le abbiamo fatto l'infusione di martedì e poi entro venerdì, sai, era passata dall'essere semplicemente malata di leucemia ad avere 3 giorni di febbre molto alta, 41 gradi centigradi o 106 gradi Fahrenheit per 3 giorni. E normalmente quando hai la febbre è perché sei infetto. Lei non aveva nessuna infezione. Abbiamo scoperto in seguito che la sua febbre era dovuta al fatto che le cellule CAR-T stavano uccidendo quei 2 kg di tumore. E nel giro di pochi giorni è passata dall'avere il cancro in tutto il corpo a non avere più cellule tumorali che potessimo trovare. Ma quasi la uccise, fu una reazione così violenta.
Benvenuti, io sono Massimo Polidoro e state per ascoltare il Gomitolo Atomico, il mio video podcast che va online ogni martedì sul mio canale YouTube. Se volete vedere questa puntata, oltre ad ascoltarla, la trovate su YouTube insieme a tutte le altre. E ora, buon ascolto!
Che cosa significa davvero curare una malattia che nasce da noi stessi? Il cancro che trasforma le nostre cellule in avversarie resta una delle sfide più grandi della medicina moderna. Eppure qualcuno ha provato a capovolgere la logica del nemico, chiedendosi: e se la cura fosse già dentro di noi, in attesa solo di essere istruita? Oggi in questa puntata speciale del Gomitolo Atomico, qui in trasferta a Berna, incontriamo Carl June, immunologo dell'Università della Pennsylvania e tra i pionieri dell'immunoterapia cellulare. Da più di 30 anni lavora per trasformare il sistema immunitario in un alleato programmabile contro il cancro. Con il suo gruppo di ricerca ha ideato la terapia CAR-T, un trattamento che educa le cellule del paziente a riconoscere e a distruggere quelle tumorali, creando, come le definisce lui, una vera e propria medicina vivente. La sua intuizione ha unito biologia, ingegneria, clinica in un'unica visione, ridefinendo i confini di ciò che chiamiamo guarigione. Quest'anno il Premio Internazionale Balzan ha premiato il suo contributo pionieristico nel campo dell'immunoterapia, riconoscendo l'impatto rivoluzionario del suo lavoro. Ogni anno, ormai lo sapete bene, il Premio Balzan mette in luce personalità che hanno cambiato il modo in cui noi pensiamo il mondo e noi stessi. Scienziati, quindi filosofi, artisti, studiosi che hanno spinto la conoscenza un passo oltre. In questa serie noi li incontriamo uno per capire che cosa muove chi dedica la vita a una sola domanda e perché da quella domanda nascono nuove strade per tutti. Prima di conversare con il professor June, però, ho voluto chiedere ad Alberto Mantovani, professore emerito di patologia alla Humanitas University e presidente della Fondazione Humanitas per la ricerca, oltre che membro del Comitato Generale dei Premi Balzan, di raccontarci perché questa ricerca rappresenta una svolta nel modo in cui intendiamo la medicina del futuro.
Grazie professor Mantovani per essere qui con noi. Allora ci spiega chi è Carl June e qual è il cuore del suo contributo?
Carl June è un medico innanzitutto, è un medico che lavora negli Stati Uniti, a Pittsburgh, ma è approdato a Pittsburgh dopo un percorso personale di ricerca con molte svolte. Ha lavorato a Ginevra, all'Organizzazione Mondiale della Sanità, occupandosi di malaria. Si è poi occupato di HIV, di AIDS e poi lui è un ematologo e un oncologo per formazione, si è occupato di raccogliere la sfida dei pazienti con leucemia e linfomi che non curiamo con le armi tradizionali. Ha osato utilizzare cellule per combattere questi tumori. Ha dato un contributo fondamentale a inventare una terapia cellulare che forse un po' tutti conosciamo, sono le cellule CAR-T, che vuol dire prendere le cellule T. Le cellule T sono i direttori dell'orchestra immunologica e le cellule che possono avere licenza di uccidere, armarle con una struttura di riconoscimento e reinfonderle al paziente. E questo ha cambiato la vita di tanti pazienti. Questo è il percorso, l'identità scientifica e il contributo straordinario di Carl June.
Che cosa ha reso il suo lavoro così distintivo rispetto ad altri ricercatori sul campo?
Noi sappiamo da tantissimo tempo che le cellule del nostro sistema immunitario tutti i giorni eliminano cellule tumorali o cellule a rischio di diventare cellule tumorali. Sappiamo da tanto tempo che le cellule T possono uccidere le cellule tumorali in vitro e in vivo nell'organismo. Ecco, lui ha osato pensare di prendere le cellule T che in un paziente sono addormentate e silenziate, rieducarle ingegnerizzandole e immietterle nei pazienti, prima in 3 pazienti adulti e poi nei bambini. E il suo contributo è straordinario. Pensiamo alla leucemia linfatica acuta del bambino. La leucemia linfatica acuta del bambino viene guarita in circa l'85% dei casi con le armi tradizionali. Ecco, lui si è occupato di quelli resistenti e ha trasformato questa leucemia resistente alle armi tradizionali guaribile grazie a un'iniezione di cellule CAR T.
In che modo la sua ricerca ha cambiato o potrebbe cambiare il modo in cui noi comprendiamo il mondo?
Siamo entrati grazie alle sue ricerche e alle ricerche di altri. Ricordiamo sempre che abbiamo sempre qualcuno che ha un ruolo fondamentale, ma ci sono tanti altri che contribuiscono. Le ricerche di Carl June ci hanno fatto entrare in un mondo nuovo, che è il mondo delle terapie cellulari. Noi abbiamo fatto progressi straordinari utilizzando come farmaci composti chimici semplici, molto piccolini, per esempio l'aspirina, tutti la conosciamo, l'acido acetylsalicilico. Poi abbiamo imparato a usare delle molecole molto più complicate, le chiamiamo farmaci biologici, per esempio gli anticorpi, che utilizziamo per curare malattie che vanno dal cancro alle malattie autoimmuni all'emicrania. Ecco, e questo è un livello di complessità 1000 volte più grande. E qui c'è un livello di complessità ancora più grande. Siamo entrati in un mondo che è il mondo delle terapie cellulari, cioè di farmaci viventi. È qualcosa che non era mai successo prima.
Il premio Balzan riconosce spesso ricercatori che uniscono rigore e visione. Ecco, in che modo Carl June rispecchia questi due aspetti?
Il rigore è una caratteristica di Carl June, e al rigore aggiungerei la tenacia. E sono due cose che vanno spesso insieme. Un rigore che lo caratterizza fin dai primi studi fatti a Ginevra su un argomento completamente diverso, che era la malaria. Ecco, mi piace aprire una parentesi: spesso la ricerca scientifica è fatta di grandi curve, di grandi cambiamenti, e le scoperte in un campo fertilizzano un altro campo. Questa è la cosa straordinaria della ricerca. Quindi il rigore metodologico, il mettere a punto metodologie nuove, la tenacia, perché quando Carl June ha sviluppato la prima terapia con cellule CAR T, c'era grande scetticismo al punto che non aveva finanziamenti pubblici per questa ricerca negli Stati Uniti. E a questa la visione di dire, sappiamo che queste cellule, le cellule CAR T, sono dei killer, dei buoni killer potenziali, ingegnerizziamole e utilizziamole, a dispetto di insuccessi e di inciampi. E quindi visione, rigore, tenacia.
Secondo lei, professor Mantovani, perché è importante oggi sostenere ricerche come quella di Carl June?
La ricerca è fatta da salti in avanti e poi da cammino lungo la via, è un po' come scalare una montagna, dove ci sono passaggi più difficili e poi invece passaggi più normali. Ecco, le ricerche spesso in immunologia ci sono state delle rivoluzioni. Quest'anno, per esempio, ricorre il cinquantenario della messa a punta degli anticorpi, di una metodologia che sono quella degli anticorpi monoclonali, cioè la capacità di produrre anticorpi diretti contro un bersaglio e produrli in quantità illimitata. Noi in questo momento usiamo anticorpi per trattare malattie che vanno dal cancro alle malattie infettive, alle malattie autoimmuni, all'ipercolesterolemia, all'emicrania. Una rivoluzione. Questa di Carl Jung, di nuovo una rivoluzione che consiste nel fatto di fare biologia sintetica. Non spaventiamoci dal termine biologia sintetica, non si tratta di generare mostri, si tratta di ingegnerizzare le nostre cellule in modo che vadano a colpire il bersaglio che vogliamo colpire, in questo caso i tumori del sangue. Speriamo in futuro anche i tumori solidi e altre cose.
La scelta delle aree del Premio Balzan riflette spesso le sfide e le priorità della conoscenza contemporanea. In che modo l'area di studio di Carl Jung riflette queste sfide?
Il Premio Balzan dato a Carl Jung risponde a almeno 2 o 3 ordini di sfide. La prima sfida è quella di utilizzare le cellule come strumento di intervento. Questo è qualcosa che abbiamo fatto un po' tutti in sistemi diversi, anche chi sta parlando, ma nessuno aveva osato farlo con una terapia ingegnerizzando le cellule, quindi osare quello che normalmente non si osa fare. La seconda dimensione è quella della resistenza. Se ci pensiamo, una delle sfide che attraversa tutta la medicina è quella della resistenza. Siamo confrontati con la resistenza agli antibiotici, apro una parentesi, tempo di influenza, non usiamo antibiotici quando non servono. La sfida della resistenza ai farmaci con cui trattiamo le malattie autoimmuni, la sfida della resistenza delle ipercolesterolemie resistenti alle statine e ai farmaci tradizionali. Ecco, Balzan riconosce il contributo che hanno dato e speriamo daranno le cellule CAR-T a trattare i pazienti che hanno tumori resistenti alle armi tradizionali. E poi abbiamo una sfida di cui non conosciamo la dimensione ed è la sfida dell'ignoto, ed è la sfida di utilizzare questo tipo di approccio di biologia sintetica e di farmaci viventi per malattie diverse dal cancro.
Ecco, faceva riferimento ad altri ambiti rispetto a quello oncologico. A che cosa si riferiva di preciso?
C'è una classe di malattie in particolare che rappresenta una sfida e che mi è molto cara come immunologo, e sono le malattie autoimmuni, in cui il nostro sistema immunitario sbaglia bersaglio e si dirige contro noi stessi. Sono malattie straordinariamente importanti perché colpiscono una quota molto importante della popolazione, fino al 20% della popolazione, e sono malattie straordinariamente importanti perché sono il paradigma di una patologia di genere, perché colpiscono di più le donne degli uomini. Ebbene, noi abbiamo fatto grandi progressi nel trattare le malattie autoimmuni. Abbiamo visto i pazienti con artrite reumatoidi che non camminavano, in carrozzella li abbiamo visti camminare, ma abbiamo una quota di pazienti che sono resistenti e soprattutto non guariamo i pazienti con malattie autoimmuni. Ci sono dati iniziali in alcune malattie autoimmuni che sono estremamente incoraggianti sulla base dell'uso delle cellule di Carl Jung, che in qualche modo speriamo di poter utilizzare per fare un resetting, come in un computer, fare un resetting del sistema immunitario e rieducarlo a non autoaggredirci. Questa è una grande, grande speranza.
Beh, grazie, professor Mantovani, grazie davvero.
È stato un piacere.
Siamo quindi pronti per ascoltare Carl Jung qui a Berna, dove riceve il premio, per capire come si addestra il corpo a difendersi da sé. Nella nostra conversazione, lo vedrete, parleremo di come la guarigione di un solo paziente abbia cambiato il corso della ricerca sul cancro, di cosa serva per guidare cellule viventi con precisione e di come la medicina stia imparando passo dopo passo a collaborare con la vita stessa. Thank you, Professor June, for being here. It's a pleasure to meet you.
Likewise, thank you.
So let's start with the question that everybody has in mind. So cancer is still among the top causes of death worldwide. And yet researchers has never offered more reason for hope. So how close are we to turning cancer into a treatable condition?
When I went to medical school, cancer was not the number one cause of death. We have to remember how things have changed. It was heart disease. And when you look at, when my grandparents were born in 1900, the number one cause of death was infectious disease. It was before antibiotics.
Yes.
So in 50 years, it went from infectious disease to heart disease. And now number one cause of death in most states in the United States is now cancer, which is what you're asking. And, in one step, it's to make it, like you said, a controllable disease, but what we would really have is like to have it cured.
Yeah.
And I think that's, in the future. I'm really optimistic about that.
You are. That's good news. Can you help listeners understand what immunotherapy is? Maybe explain it as if you were talking, as we said, to a smart friend who knows nothing about biology.
So immunotherapy is, the public understands vaccines. The COVID vaccine taught a lot of people about spike and antibodies, and you need T cells in order for the vaccines to work. So vaccines are, that is a form of immunotherapy. The idea of cancer immunotherapy was probably best and first started by Paul Ehrlich in Germany in about 1860. And this is right around when microscopes were being used to look at cancer cells and tumors from patients. And they saw sometimes in the cancer, they would see small blue cells, which turned out to be T cells. They didn't know back then, but Ehrlich imagined that there was a fight, a tug of war maybe between the cancer and some cells that might be trying to stop it. And he actually drew pictures of what he called magic bullets. And this was before we knew what an antibody was, what T cells were. But his actual drawing of how an antibody, this magic bullet that he drew, was really quite accurate for when we finally got the structure of antibodies in the 1970s. It was amazing. So he was 100 years ahead of his time.
Wow.
And so we had the ideas of cancer immunotherapy, the magic bullets, but then it was more than a century until it happened. And that's an important thing for, I think, the public to understand, that science goes, you can have ideas and then sometimes you're dependent on technology to make them real. And so the idea of immunotherapy was old. And then many experiments were tried. People actually, in the United States in the 1920s were taking bacteria, because sometimes surgeons would operate on someone with a cancer. And if it got infected, sometimes the cancer would go away. So then William Coley was a surgeon. He made cultures of bacteria and actually intentionally injected people, and they would get high fevers, but occasionally the cancer went away. That was called Coley's toxins, but it never got FDA approved. So then people gave up on that, and it wasn't until monoclonal antibodies, and really the kinds that Ehrlich had proposed in the 1860s. In 2011, the first one was approved for a cancer therapy, and that was called ipilimumab for metastatic melanoma, a cancer, skin cancer that's often lethal, and that resulted in a Nobel Prize going to Jim Allison. And actually, Jim Allison and I both got, in 2014, the Paul Ehrlich Award in Germany. And we both sat in Paul Ehrlich's desk, where he had been in Berlin and later in the Munich area. So that was a really, to me, sort of a full circle event of seeing how the idea of immunotherapy finally became real. So that was the first FDA-approved cancer therapy. And then, we began working on CAR T cells as a cancer therapy.
So as you were saying, this idea was like sort of a fringe science up to a point, to many. And then what made you believe it could work when others had given up? What was the spark?
Yeah, so, cancer therapy had, for 50 years, people tried it, the cholestoxin, and never worked in trials that could come, make it into the day-to-day practice of cancer, which was really what it had been for 50 years. Chemotherapy, then radiotherapy in the 1920s, chemotherapy in the early 60s, and surgery, which has been going for centuries. That's what we had. And then, so there was no industry to do cell and gene therapy, which is what CAR T cells are. And we started really just as an academic experiment. Could we take cells of the immune system, the T cells that normally fight viruses, and could we reprogram them so that they could also kill cancer cells? And it was really just an academic experiment, and one of the rare times in science where in humans it actually worked better than it ever did in our mice. I mean, almost always it's the other way around. Almost all cancer therapies tried in mice that work great in mice don't work when you do the real test in humans. And in our case, the very first patient was cured. It was just one of these true paradigm shifting things where the first 3 patients we treated all responded, and all of a sudden something that everyone said would never work, you're crazy to work on this, all of a sudden they said, oh, that was a great idea all along.
Of course.
Yeah.
Can you explain to our listeners how CAR T therapy actually does work?
Yeah, sure. So CAR T therapy, first of all, CAR stands for chimeric antigen receptor. And chimeric because it's a fusion between 2 major cells in our body, the B cells that make antibody and the T cells that normally kill viruses. And so the idea was to in the Greek thing where you fuse different animals together to make a chimera, here it's a fusion of the 2 basic immune cells in our immune system. And, so that had been done in Petri dishes in the late 1980s as a basic science experiment, but no one had ever really thought it could be a therapy. And over about 20 years, my group learned how to grow T cells. We actually first tested this in AIDS patients in the 1990s and had success with, making chimeric cells in patients. And then, but we had a lot of trouble getting funding to do trials in humans. But the basic idea is we can use gene transfer technology to, insert the gene that makes an antibody, which is what B cells make. And we all learn about that from COVID vaccines. And now your T cells can make them too. So it gives them, I like to say, 2 jobs. They have their day job, which T cells in our bodies normally fight viruses. And if you lose your T cells, you die. I mean, that's what the AIDS epidemic taught us, because the AIDS virus kills T cells. And then if you lose all your T cells, you die. So you have to have them. And then what we do is give the T cells with the gene transfer technology, what I call a nighttime job. And that's to be able to kill cells that have a certain flag on them that's just on their tumor cells.
Yeah. So one CAR T cell can kill around 1,000 cancer cells, right? So what happens when a body, once the CAR T cells begin circulating in it? What happens to
them? So our body, and we learned this from the AIDS epidemic, has almost a pound of T cells in you. And if you look up in Wikipedia, that's about 1,000 10 to the 9th cells, a billion cells is it's 1,000 billion, so that's 10 to the 12th. That's what we have. And what we do is take some of the cells out of the body and your blood. Only about 1 or 2% of all your T cells are in your blood. So we take those out, and then in the laboratory of over about 2 weeks, we transfer the gene that makes them into a CAR T cell, and then give them back to the patient. And what we infuse in the patient is like a drop, just a tiny drop in the pool of all of the T cells we have. So we infuse about 100 million T cells, so that would be 10 to the 8th. And then it's, as you said, they multiply about 1,000 times in the body. So 10 to the 8th becomes 10 to the 11th. So CAR T cells in your body, and that happens within 2 weeks. It's an amazing thing. Your body actually becomes a bioreactor, so they take root in your body and grow. And when the major principle of a CAR T cell is when it binds to a tumor cell, it does 2 things. First of all, it recognizes the tumor and says, you're a bad guy, you should be dead, and it kills it. But then the CAR T cell divides, and it has 2 daughter cells. So then it becomes, mathematics, just 2, 4, 8, 16, 32. And if you divide, 5, 6, 7 times, pretty soon you're 1,000. And then that's how they're what we say self-amplifying or serial killers. One CAR T cell can kill, and their daughter cells, one of the daughter CAR T cells, can kill many tumor cells, but then they live in the body as memory cells. And that's why it's the first living drug. Okay. Our first patients treated in 2017 still have CAR T cells now, about 15 years later.
Take us inside that moment in 2012 when you treated Emily Whitehead, the first child to receive CAR T therapy. What was going through your mind?
Well, so at that time, we had treated 3 adults. We started in 2010 with the CAR T cells, and all 3 had responded. With Emily Whitehead, we didn't know what dose to give. And it turns out the T cells in children are more potent than adults. And in Emily, we infused her. She at that time had about 5 pounds of tumor. And she only weighed about 60 pounds. Wow. So a big part of Emily at that time was cancer. And it was in her blood, and her bone marrow, and her liver and spleen. It was all over. And, she'd had her cancer come back 3 times. And basically they had said it's time to go home, be on hospice therapy. So she ended up being the first pediatric patient on our trial. And we thought it had failed. In fact, we thought we might have killed her because we infused her on a Tuesday. And then by Friday, she'd gotten from being just sick with leukemia to where she had 3 days of a very high fever, 41 degrees centigrade or 106 degrees Fahrenheit for 3 days. And normally when you get fever, it's because you're infected. She had no infection. It was, we found out in retrospect, her fever came because the CAR T cells were killing those 5 pounds of tumor. Wow. And in the space of just a few days, she went from having cancer all over her body to being no cancer cells we could find. Wow. But it almost killed her. It was such a violent reaction because the body, that causes inflammation, when you destroy that many cells at one time, we were lucky that we found a way to treat it, and it was called cytokine storm that she had, this 106-degree fever. And so when we treated her with an antibody to block the high fever, the antibody is called tocilizumab, she woke up from a coma and the cancer was gone. Yeah, we didn't believe it. I mean, it was one of those miraculous moments where, in a biblical sense, it was like Lazarus. Lazarus was given up for dead and comes back. We had thought she was going to die. They had called her family to bring in all the relatives that it was time to say goodbye.
I wonder what her parents thought at the moment when they realized that she was free from the cancer. Wow, what a moment. A few personal questions, if you don't mind. When Time listed you among the 100 most influential people in the world in 2018, you said your kids were more impressed than you, especially when they saw you ranked ahead Jennifer Lopez or Rihanna. How did that feel to you, though?
Well, so as an academic, that it's a job that has many hours, and I was often gone when my kids were young, and missed a lot of the soccer games, and and they really, I would talk about my wife, who was also trained as a scientist. We would discuss the experiments that were happening, and they basically never paid attention until that Time magazine came out, because they knew who Jennifer Lopez was.
Yeah, of course.
And so it was really, and then they paid attention. I mean, it was, it's been an amazing journey since. So we treated Emily Whitehead in 2012. I went down to the White House with her when President Joe Biden was president, and he met her. And also when Obama was president. And a funny story there was, we had, at that time, this was 2015, it was 3 years after Emily had been treated. So she was, at that time, 9 or 10 years old and, going to primary school. And it was a Monday in the end of January, and the White House had just announced they were starting. This is very different if you understand our current politics.
Of course.
But they were starting a new initiative in precision medicine, and they were going to give more funding because of the progress they were seeing. So they invited Emily Whitehead to the White House as living proof of that. And so we then had Obama announced it, press cameras, all these press photo ops, and then they had a receiving line, and Emily Whitehead's father is Tom Whitehead, and they were going through the receiving line. And when Obama shook his hand and saw Emily there, he said, "Is there anything I can do for you?" And Tom Whitehead said, "Well, yes, as a matter of fact, she's supposed to be in school today. Could you write her an excuse to get out of school because it was Monday?" And Obama did that on White House stationery, and it's in the movie. He says, "Please excuse Emily. She was with me today."
Fantastic.
Yeah.
If we go back to your beginning, you grew up in a military family during the Cold War. And how did that shape your worldview and did influence your later approach to fighting cancer?
Yeah, so I actually didn't grow up in a military family, but I ended up in the military.
Oh, you ended up, okay.
And that was because of the Vietnam War. And when I finished high school and was going to go to college, they had in the United States a draft, a random lottery based on your birth date. And mine draft number came up in 1971. I would go into the Army, into Vietnam, into the rice fields. So I had been admitted to Stanford, and I thought I was going to be a chemist like my father. And instead I went into the Navy, and it turned out to be very fortuitous. And so I learned to the Naval Academy. I went to Vietnam for one summer, but the Vietnam War got over, and then the Navy paid for me to go to medical school. And that was something I never thought I would do. And it turned out to be, I loved medicine. And then in one of these other quirks of fate in the 1980s, once, after the Vietnam War got over, at that time, then it was really the big issue was the Cold War with Russia and, nuclear détente. And the U.S. Navy had many submarines, and they wanted to have a therapy for limited nuclear casualties, like Fukushima, for instance, in Japan. And so I was trained in bone marrow transplantation, which was the one therapy potentially for that in the 1980s. And then, I was going to open a bone marrow transplant unit for the Navy in Bethesda at the Naval Hospital. And then in 1989, the Berlin Wall came down and there was no more Cold War. And the Navy didn't care about having a bone marrow transplant unit anymore. And, we downsized our military with the end of the Cold War. And then the Navy let me work in the laboratory. And so I worked on what the Navy funded, which was research in infectious disease. So I worked in Switzerland here on malaria immunotherapy, and then I worked on AIDS when that epidemic came out, and that's led to CAR T cells. So it was a very circuitous set of changes in political aspect of international policy and so on that let me end up working on T cell therapy initially for AIDS. And then when I got out of the military in 1999, I went to the University of Pennsylvania and started working on leukemia.
You've said publicly that losing your wife to cancer changed your research focus. Can you tell us how?
Sure, yeah. So my first wife had, we had 3 children, and she one day came back from jogging and felt pain in her stomach, and it was ovarian cancer. Just a bolt out of lightning out of the sky. And so I was trained as a leukemia specialist. And but I became then a caregiver for her as a medical oncologist. But I had never seen what we would say the other side of the bed, what it's like to live with someone undergoing high dose chemotherapy, bone marrow transplant, and it was much worse than I knew. I tried to get an immunotherapy for my wife. I made a cancer vaccine for her, and I think it prolonged her life. And then. But she ended up dying 5 years later. And that experience of knowing what we could do in mice for cancer therapy, but I found out how hard it was to get it into an experimental trial. So then, in my laboratory, I'd been actually, as I mentioned, working on HIV cell therapy, but it was always kind of like the back burner project where the number one goal was really more basic science of immunology. And then, so after that experience with my first wife, I began putting, the experiments in humans up into the number one priority. That really changed my priorities. And I got remarried and now have 5 children
wow.
from the 2 different wives. Yeah. So I learned a lot from that experience. And that still is a very big problem. We have this bottleneck of really amazing throughout the field of science right now of very promising therapies for many diseases, and yet the bottleneck is it's very expensive and time consuming to test them in human trials.
Yes, as you mentioned, it's very expensive. A treatment can cost $500,000. Is that correct?
Yep.
So how do you wrestle with creating life-saving treatments that many cannot afford?
Yeah, so the way I look at it is with all new technology leaps, they're initially restricted really to the wealthy and they're expensive. So the initial first cell phones, I remember, I couldn't afford one. And then now almost everyone has one. And that is because of industry working, and they got better and cheaper. And the same thing happened with computers. So technology, when you have it, is initially more expensive, and then it will get cheaper. So that's one answer, is that I think the pharmaceutical industry is going to learn how to make these personalized therapies much more economically. But there's also in addition to the cost of the current therapies, we have now new ways of making CAR cells. Well, instead of taking them right out of your body, we can make the CAR T cells in your body. And then right now, the most expensive part of this loop is you get your own cells from your blood, ship them to a manufacturing center, and then they're manufactured. In this case, in Europe, it would be in Basel, and then where Novartis is. And then they would be shipped back to the physician and the patient. That's a very expensive loop.
Yeah.
And it doesn't exist for other kinds of therapies. And that whole manufacturing logistics can be much simpler if you just inject and make the CAR T cells right in your own body. And that, I think, is on the horizon within the next 5 years.
You have seen both the slow pace of academic research and the speed of biotech. How do you see the relationship between public and private research in bringing new promising drugs into society?
Yeah, so, we need, traditionally, the pharmaceutical industry is needed to do the kind of large-scale trials that prove something works, and then to make things very carefully for us. But traditionally, innovation and breakthroughs and new therapies come in academic arenas in universities, and that's true in Europe and the US and now in China. And so the pharmaceutical industry oftentimes makes what are called Me Too drugs. So once a new drug has been made, they can make new ones that are similar and may have better properties, but they're not usually a brand new kind of drug. That usually innovation and leap forward happens in academia. So that is a partnership that's very necessary. We need to have basic science, and I can, my own experience, the first CAR T cells we tested were for HIV. And that was because during the initial AIDS epidemic, there were no drugs. And we needed a way to grow back T cells in patients because the virus killed that. And then it turned out because of that research we had done in HIV, we were able to make CAR T cells for cancer patients. And then now that's something that happens all the time. So, but all that development was done in an academic arena and funded by government research. And that is something really important. There's larger research budgets in the pharmaceutical industry, but in general, what really makes new breakthroughs is the kind of research that happens by scientists in laboratories across the world.
How do you see the situation today?
Yeah, well, right now, we have, the situation today in the U.S. is very frightening. We had in March and February of this year, the president's budget was a 40% cut to the funding of science in the United States. And we still don't know all the impact of that. What I can tell you is it's drastically impeding the ability of new scientists. So I have a laboratory of around 30 graduate students and postdocs in Philadelphia at the University of Pennsylvania. And this year, 4 of them have left the United States to go back to Europe.
Wow.
And then 2 of them to Italy, and 1 to Germany, and 1 to France and Paris. They would have stayed in the United States, but because of the political, right now, atmosphere, which is not very encouraging if you're a junior scientist, because you have to have some prospect of funding.
Absolutely.
So they left. So it's really going to impact and have long-term negative implications for the workforce, because we need to have new young scientists. There's many promising areas of science now that need people to go into this field. And unfortunately, in the United States, it's not a good time for that to happen.
We had a brain drain from Europe towards the United States, and now we're seeing it.
Yes. So for many years, I benefited in the United States by that because there was more funding in the United States than there was in Europe. And so we could attract in, like I have about half my laboratories from Europe. And it's a really lovely international mix of US and European, young scientists. And now we're seeing this reverse brain drain. In fact, I just was awarded a large grant from the European Research Commission, and it's with the University in Heidelberg.
Yeah.
And so for the next 5 years, my laboratory in Philadelphia will be working closely in Heidelberg. And that's because there's actually more funding in Europe now than there is in the United States.
Wow. Have you ever counted how many people you have treated so far?
Well, not my own lab. So CAR cells are unlike a lot of other therapies where there are ongoing trials in academia And so that, when you want to know the total denominator of patients treated, it's a sum of those treated on academic trials and those treated with a commercially approved products. And then there's the fact that now there are over 1,000 trials across the world, with most trials in actually China, US, Europe, very few in the Southern Hemisphere other than Australia. But the estimates are 45 or 50,000 people have now been treated. And it's a number that's going up very rapidly.
How do you feel when somebody is finally treated?
That's a very rare opportunity, I think, for someone in their own lifetime to see benefits from something they may have done. I mean, because many times you never know. It's oftentimes talked about Mendel.
Yeah.
So Mendel, invented genetics. He did these experiments with peas and showed that something allowed heredity to happen, and that it could be passed on from generation to generation.
Yeah.
And he was never recognized until the 1900s.
Exactly.
And so I've been very lucky to have something that started in my own laboratory actually become something useful in my own lifetime, and it's an immense privilege to watch.
What are the frontiers now of CAR T-cell therapy?
Well, we have this large and increasing area of cell and gene therapies, and there's a tsunami of new therapies. I mentioned there's 1,000 trials.
Yeah.
So you now have many brains working on this instead of it just being in a few laboratories. And for any cancer you can think of, there are trials. And now, most amazingly, there's hundreds of trials for autoimmune disease all around the world, and it's really exciting. So we're going to see all of those come out. And I mentioned it won't be all. Right now, the complex way of making CAR cells are going to get much cheaper, and then they'll be manufactured in your own body, by injecting nanoparticles and viruses and so on. So it's such an exciting time. I mean, for the junior scientists and around, there could not be a better thing to go into now because of the exciting possibilities that new technology has made available.
As you said before, the great breakthroughs come from research that is not specifically aimed at something, and that's why it is so important to be able to do blue sky research, no strings attached. Do you already know what ideas in particular you intend to invest the funds you received from the Balzan Prize?
Yeah, so I'll tell you, first of all, things have happened just since our first CAR T, it treated Emily Whitehead in 2012. That's the year that Jennifer Doudna and Emmanuel Charpentier published CRISPR, which was the ability to then change genes at will. Well, and then it's turned out that gives us huge opportunities with CAR T cells. We can use CRISPR technology, which was an unbiased experiment in fruit flies, studying the immune system in flies, that allowed CRISPR to be developed. And then now we use it in experimental CAR T cells. So it's a very exciting time of where I think we're going to be able to make what I call synthetic T cells, where we can rewrite many genes in the genome to make a supercell that is more powerful for the disease we want to treat. And it can be very different in the case of cancer or infections, or even turning off immune systems in a selective way, like for autoimmune disease. So all of those things now are doable, and the technology is so rapidly changing that it's hard to keep up with it.
Wow. You're known for being a bicycle rider. You cycle to work and competing in long distance rides. And you said that some of your ideas come from when you're on a bike. So what does that do to you?
So, when you, exercise is a way to free up thoughts and have just, stream of consciousness happen. And I just recently had like a full circle thing where I did. So I mentioned earlier, I went to the United States Naval Academy. I started there in 1971, and then we graduated in 1975. And I ended up going into medicine, but most of my other classmates, some of them went in, became Marines, some on submarines, some pilots on aircraft carriers. But 14 of us just did a charity bike ride. That was, we went from the Gulf of Mexico in Florida all the way up to the Chesapeake Bay where the United States Naval Academy is. It was 2,000 kilometers. Wow. And so that was a charity bike ride for the Emily Whitehead Foundation.
Yeah.
And we raised $110,000 on that. And but the 14 of us, we had been together since we were age 17. Then we scattered across the world in different careers. But then for 23 days while we did this ride, we talked again like we were young children, teenagers again. Right. But anyway, it was really an amazing time for me, and just to uncouple like that, the thought of, so that exercise for me has been, it's a wonderful idea generator. So for me, it's always been a great way to and sometimes when you're dreaming, you wake up with a new idea. But to me, the exercise, like riding bikes, running, has been for me over the years really a lovely thing. It's a passion.
Passion. Yes. I have one last question for you, and for this I need to show you an image.
Okay.
So we have here a mystery box. Let's say this is a cardboard box which is sealed. We don't know what's inside. But let's imagine that you could find inside this box the answer to a problem, a question, anything that you thought about a lot in your life, and maybe you're still wondering about that. What answer would be in this mystery box?
Well, maybe the meaning of life.
Well,
but,
why not?
I mean, right now, the question that keeps me up at night is, what do we need to do so that CAR T cells work for all cancers? I mean, and the biggest cancers that right now adults, it used to be that the number one cause of cancer death in kids was leukemia. Yeah. And it no longer is. And that's because of CAR T cells, and many cases are cured. So, but in adults, the main awful things that haven't changed since my medical school days are like brain cancer, pancreatic cancer, are really very little change. And so that mystery box for me is, what do I need to do to a T cell to make it be able to cure pancreatic cancer or brain cancer?
So the second question is, if you had such a box with the answer, would you open it, or would you prefer to find yourself the answer?
Pandora's box. Yeah, I know. No, I think I would open it because we really need to do this. It's it's an emergency right now to get a cure for cancer.
Thank you very much for being with us.
Well, thank you. It's really been a joy to talk with you on this. Thanks. Okay.